In this video, we're going to talk about trends in atomic and ionic size in the periodic table. So if you imagine the periodic table, if you go across a period, you're really going from left to right. So as you go from left to right, what happens is the atomic number increases, which means the number of electrons also increases, but the electrons keep getting added to the same level. So what we mean by that is, let's take for example, let's say we're in group 2, we're in period 2. Period 2 starts with lithium, and then you have, beryllium, and then after beryllium, you get to boron, then carbon, then nitrogen, then oxygen, then fluorine, and then neon. Now, if you try to write out the electron configuration of all of these, you will see, if I just take a look at the valence shell, essentially what happens is, in lithium you have 2s1, beryllium is 2s2, boron is 2p1, and then 2p2, 2p3, 2p4, 2p5, and 2p6. Notice carefully, the additional electrons are just getting added to the same sublevel from boron to neon, and the same sublevel from lithium to beryllium. Notice carefully, that's a different sublevel, it's S and P, but if you look at the level, 2, 2, 2, 2, 2, 2, 2, 2. So across a period, you're in the same level. What this means is, if you imagine the atom, that's the nucleus, you have these shells. These are the levels, so level 1, level 2, so that's the principal quantum number, level 2. So all these electrons are getting added to the same level, which means what's happening is, to balance the charges on these electrons inside the nucleus, for every additional electron you're adding out here, so let's say you have 10, you added another one, 11. For every additional electron, now you're adding an additional proton, right? So now you have more positive charges attracting more negative charges. These are all the negatives, and these are all the positives, okay, from the protons. For more positive charges, you have more negative charges, and the distance is not really changing, which means you have more stronger charges attracting each other, which means it effectively shrinks the atom. So as you go from left to right across a period, what happens to atomic size? It decreases. Now, atomic radius also decreases, because essentially, if you think of the atom as a sphere, the radius it follows the same trend as the size. If the size increases, the radius increases. So atomic size or radius also decreases. Now, if we compare, let's think about what if we change this to a cation? Same logic. For cations or anions, the logic is the same. So logic is the same. As you go from left to right, the size will decrease. Now, there's one little weird thing out here. If you compare an anion with the corresponding atom, so let's take, for example, let's not take nitrogen. Let's say we compare oxygen, okay? So we have the oxygen atom, and we're comparing it with the oxygen anion. So that's the anion. So the difference between the oxygen atom and the oxygen anion is, the atom actually has 8 protons in the nucleus and 8 electrons outside. So 8 protons attracting 8 electrons. Out here, you actually have 8 protons and you have 10 electrons outside. Okay? So 8 protons attract the 8 electrons, and then you have 2 additional electrons, and those 2 additional electrons don't feel an additional pull, because the net pull is kind of decreased compared to this, because you have the ratio out here is 1 to 1, and the ratio out here is less than 1 to 1, okay? And because of that, you have a little lesser pull. So as a result, because they're pulled less inside each other, they kind of expand slightly. okay? So therefore, an anion of the same element, so anions of the same element, it's important for it to be the same element, okay, are larger than the atom. If you take a look at cations, so let's take for example sodium, that's the atom, versus the sodium ion, so that's a cation, okay? So out here you have 11 protons and 11 electrons. Out here you have 11 protons, but you only have 10 electrons. So now you have fewer electrons, so therefore these electrons are going to experience a greater amount of positive charge from the nucleus. So therefore what's going to happen is going to shrink it more. So therefore cations of the same element are smaller than the atom of the same element, okay? So it's important to understand kind of these trends. So now that we understand the trends as you go across a period, let's take a look at the trends, what happens when you go down a group, okay? So if you kind of, if I go down this group, so lithium, below lithium I have sodium, below sodium I have potassium, and then I can keep going down this group. But essentially, if you just look at compare, and let's say above lithium I have a hydrogen, so the atomic number, so Z is 1 for hydrogen, for lithium it's 3, I'll just circle them, for sodium it's 11, for potassium it's actually 30, it's 39, okay? So now as you can see, the number of protons are increasing significantly. But what else is increasing? The number of electrons, okay? Now, but where are those electrons coming in? So in the case of lithium, they're coming in the principal energy level 2, which is this energy level out here in this atom. But in the case of sodium, they're coming in 3. In the case of potassium, they're in 4. We need to create another one for potassium. So as you can see, the shells, the layers beyond the nucleus are increasing as you go down a group. So as you go down a group, because the layers are increasing, it's not just about additional electrons and protons, but the distance of the electrons, the additional electrons, is also increasing from the nucleus because they're in new energy levels. And as a result of that increased distance, you have an increase in size. So therefore, as you go down a group, size increases.